This is lecture 7, sensitivity analysis for IE 3340, operation research. In this slide, I want to go over the course objectives and discuss how, at this point of the semester, how are we in terms of covering them. So we start our course with a review on linear algebra, and then we transition into an introduction to LP or linear programs model formulation. Then we transition to solving problems using the graphical method, solving LP. And from there, we transition to LP model formulation for real-world problems, in which we discuss formulations for production planning, resource scheduling, and oil refinery. And lately, we've been working with the LP algebraic solution by applying the simplex algorithm, which is connected to the discussion that we have at the beginning of the semester about linear algebra and the use of the Gauss-Jordan method. We also have discussed how to solve linear programs using the computer, specifically Excel and AMPL. And I want you to see how our course objectives are being fulfilled in terms of considering real world problems and determining whether or not linear programming is an appropriate modeling framework. Also develop linear programming models that consider the key elements of real world problems, solve the models for the optimal solutions. And in this lecture, we're gonna start looking at that fourth objective, in which we need to interpret the model solutions and infer solutions to the real world problems. So what are the learning objectives for this lecture? First, we want to discuss how changes in an LP or linear program parameters affect the optimal solution. That's what we call a sensitivity analysis. Also, we want to explain how to use the Excel server output to answer questions of managerial interest, such as what is the most money a company will be willing to pay for an extra hour of labor? So this lecture is divided in 3 parts. First, the graphical sensitivity analysis, in which we are going to look at a small problem with 2 decision variables, and we are going to apply the graphical method, and we're going to explain how the solution and how changes into the model affect the solution for our problem. And then we can see the impact of changing some of the parameters into the model, and we can answer questions related to, from a managerial perspective, how those changes are impacting our goals. Then the second part is the algebraic sensitivity analysis, which has the same idea, but the algebraic version of the sensitivity analysis is looking at problems that have more than 2 decision variables. And finally, the third part is how to generate a report from Excel to answer questions using sensitivity analysis. So in this video, we're going to focus on the first part, which is the graphical sensitivity analysis for the right-hand side of the model and the objective function. So during the first 6 weeks, we've been focusing on modeling linear programs, solving these linear programs graphically, and also using the simplex method. In our previous lectures, we also look at how to use artificial solutions to find initial solutions so we can apply the simplex method. So subject matter of this lecture In LP, the parameters or the input data of the model can change within certain limits without causing changes in the optimum. So what this means is once you find an optimal solution to the problem, there are some parameters that you can change, increase or decrease, and you will still have the same optimal solution. So the optimal solution will not change. So the idea is to find those ranges of values in which you can vary your parameters and keep the optimal solution. So you know if you want to increase this many hours of labor, if that has an impact in terms of how much revenue you will have, but still you keep that optimal solution. So this lecture explains the basic ideas of sensitivity analysis. So let's start with the graphical sensitivity analysis. This section demonstrates the general idea of sensitivity analysis using graphical methods. Two cases will be considered. First, the sensitivity of the optimal solution to changes in the availability of the resources, which is basically the right-hand side of the constraints. That's what's limiting our capacity. So we're going to see how changes in the right-hand side of the constraint or what is the sensitivity in terms of the optimal solution and the availability of resources. The second case is the sensitivity of the optimal solution to changes in unit profit or unit cost, which basically means that we want to see if we increase the price or the revenue, how sensible is our solution to those changes. So we are going to look at an example in which we have production lines, just like this one. So we have different lines and we want to ask questions about how to improve our efficiency. So we have Jeffco manufactures two products on two machines. A unit of product one requires 2 hours of machine one and 1 hour of machine two. And for product two, one unit requires 1 hour of machine one and 3 hours on machine two. The revenues per unit of product one and two are $30 and $20 respectively. And the total daily processing time available for each machine is 8 hours. So to formulate this problem, we can state our decision variables for a unit or units produced of product I. The objective function is going to be based on the revenues. So we want to maximize that revenue. So maximize Z equals to 30x1 plus 20x2. And this is going to be constrained to these hours, 8 hours for machine one and machine two. So the time takes to produce part one plus the time takes to produce part two on machine one has to be less than or equal to 8. So this is for machine one. And then for machine two, we have x1 plus 3x2 less than or equal to 8. This is machine number two. And don't forget the non-negative values for our decision variables. So if we plot the constraints in this model, we can see what is the feasible region. So you're familiar with that. So that is our feasible region. And in this problem, the optimal solution is this point C. So you find that point using the isoprofit line. So x1 equals 3.2, x2 equals 1.6 is going to be generating a revenue of 128. The new graphs illustrate the change in the optimal solution when changes are made in the capacity of machine 1. So for example, if we increase the right-hand side of the first constraint by 1 unit, that line is going to move towards the right. Okay, so if you draw, let me go back here. You find the isoprofit line for this it will look something like this. So the isoprofit line will be like this. And that's how you identify this point C. So if you move that line in this direction, the last point that that line is going to touch is point C. So if we increase by 1 unit the capacity of machine 1, this constraint is going to move 1 unit towards the right. Okay, so that new constraint, or that movement of that constraint, is now increasing the feasible region. So the feasible region now also includes this area. And if you use the same isoprofit line that we draw, you know that as you move that line in this direction, this is the last point that is going to touch in the feasible region. So so that's going to change the optimal solution. If the daily capacity is increased from 8 hours to 9 hours, the new optimum will move to point G. The rate of change in optimum resulting from changing machine 1 capacity from 8 hours to 9 hours can be computed as follows. The rate of revenue change resulting from increasing machine 1 capacity by 1 hour, point C to point G, is going to be equal to the slope or derivative. It can be computed as follows. So is the Z value for that G point minus the Z value, or the optimal solution value for C, divided by the capacity change. So this is gonna be 142 minus 128 divided by 9 minus 8. So that is equal to $14 an hour. So what this is stating is that each additional hour of machine 1, or increasing machine 1 time, increases revenue by $14. That is what we call our dual price. That is the price, or the revenue that you that you have, an additional revenue that you will obtain if you increase an extra hour of that particular resource. So if, for example, if it costs you $10 to increase 1 hour of labor and you are making $14 by increasing that hour, then that means that you have a profit of $4. So that in those cases, considering the increase of a machine by 1 hour or the job period by 1 hour will give you a profit of $4. But on the opposite side, if you know that it's going to cost you $20 to increase that time by 1 hour and you only make $14 revenue, then you know that it's not a good decision for you to increase the capacity of that resource by 1 hour because you're going to lose money. So those are the type of questions that we can make and answer using the sensitivity analysis. The named unit word of a resource is a description of the rate of change of the objective function per unit change of a resource. Early LP developments have coined the abstract name dual or shadow price. This name is now standard in all the LP literature and software packages. By looking at the graph, we can see that the dual price of $14 an hour remains valid for changes, increases or decreases in machine one capacity that move its constraint parallel to itself to any point on the line, segment BF. So as long as we move in that direction, we know that we are going to, as we increase 1 hour, we're going to have a dual price of $14 an hour. Same thing. So if we decrease, we're going to lose, or we are not going to make that $14 an hour. So by increasing or decreasing, that's the rate of change. That's the dual price. The name unit word of a resource is a description of the rate of change of the objective function per unit change of resource. This is the same slide. So I'm just repeating the same information. So that's what we call the dual or the shadow price. And this has been coined in the LP literature and also in the software packages like Ample and Excel. And as we mentioned already, for this machine one capacity, the dual price is $14. Now we compute machine one capacities at point B and F as follows. The minimum machine one capacity at B is going to be equal to 0 and 2.67. So 0 and 2.67 are the coordinates for point B. Machine one and the maximum machine one capacity happens at point F, which has coordinate of 8 and 0. So we can compute the machine one capacities at those 2 points by using the coefficients for the constraint for machine one. So 2x1 plus x2. This is the left-hand side of the constraint for machine one. So if we substitute those coefficients into the constraint, we have 2 times 0 plus 1 times 2.67. So that is equal to 2.67 hours. For the second point, that will be equal to 2 times 8 plus 1 times 0, which is equal to 16 hours. So the conclusion is that the dual price of $14 an hour remains valid in the range 2.67 hours. So this has to be less than or equal to the machine capacity. and less than or equal to 16 hours. Changes outside this range produce a different dual price. Okay, so if we go above or below these changes, it's going to be a different dual price because the optimal solution of the problem will change. Using similar computations, you can verify that the dual price for machine 2 capacity is $2 an hour. Remains valid for changes in machine 2 capacity within the line segment DE. We compute the machine 2 capacities at point D and E as follows. So again, we have the coordinates for D and E. The coordinates for D is 4 and 0. The coordinates for E is 8 and 0. And we are gonna use constraint for machine 2, which is x1 plus 3x2. This is the left-hand side of machine 2, or the the constraint for machine 2. And I think this should be, this is the opposite. This should be 0 and 8. So this is gonna be equal to 1 times 4 plus 3 times 0, which is equal to 4 hours. And this is 1 times 0 plus 3 times 8, which is equal to 24 hours. So the conclusion is that the dual price of $2 an hour remains valid in the range 4 hours less than or equal to machine 2 capacity less than or equal to 24 hours. The computed limits for machine 1 and 2 are referred to as the feasibility ranges. All software packages provide information about the dual prices and their feasibility ranges. So, for example, Excel and Ample will generate those numbers for you. The dual prices allow making economic decisions about the LP problem, as the following questions will demonstrate. So question 1, if JEPCO can increase the capacity of both machines, which machine should receive priority? So the answer for this question is additional hour of machine 1 increases revenue by $14 as opposed to only $2 for machine 2. Those are the dual prices for machine 1 and machine 2. So based on those numbers, we should give priority to machine 1 because we know that the revenue is going to be higher for machine 1 versus machine 2. The second question is, a suggestion is made to increase the capacities of machine 1 and 2 at the additional cost of $10 an hour for each machine. Is this advisable? The answer for this question is, for machine 1, the additional net revenue per hour will be 14 minus $10, which is equal to $4. This is what's one of the things that I was mentioning earlier. However, for machine 2, the additional net revenue will be 2 minus $10, which is minus $8. So only machine 1 should be considered for capacity increase, because if you increase the capacity of the second machine, you are going to be losing money. Question 3, if the capacity of machine 1 is increased from 8 hours to 13 hours, how will this increase impact the optimal revenue? So the dual price for machine 1 is $14 and is applicable in the range from 2.67 to 16 hours. The proposed increase to 13 hours falls within the feasibility range. Hence, the increased revenue is $14 times the difference between the increase in hours. from 13 to 8. I mean, from 8 to 13. So 13 minus 8 times 14, so it's 5 times 14 is going to be equal to $70, which means that the total revenue will be increased from $128 to $198. Question 4, suppose that the capacity of machine 1 is increased to 20 hours. How would this increase affect the optimal revenue? The proposed rate change is outside the feasibility range, which is 2.67 up to 16 hours. So further calculations are needed to find the answer, and that will be discussed in a following lecture. So as you can see, these type of questions can be answered using the information generated by the sensitivity analysis in terms of the shadow price or dual price. So now we're going to focus on that first part. We were focusing on the right-hand side of the constraints. Now we want to see how changes in the revenue units or the objective function coefficients will change the slope of the optimal solution. However, the optimal solution at point C remains unchanged so long as the objective function lies between lines BF and DE. So as you can see here, this is line DE. This is line BF. So as long as this isopropyl line remains between those two lines, if you change the slope of the objective function by changing the coefficients of the objective function, as long as that line remains between those two, between line BF and DE, then we know that the objective function and the optimal solution will not change, which is point C. How can we determine ranges for coefficients of the objective function that will keep the optimal solution unchanged and at C? First, we write the objective function in the general format. So that general format is as follows: maximize C equals to C x1 plus C x2. Imagine now that the line is pivot at C and that it can rotate clockwise and counterclockwise. The optimal solution will remain at point C so long as this Z is equal to C times x1 plus C times x2 lines between the two lines x1 plus 3x2 equals 8 and 2x1 plus x2 equals 8. This means that the ratio C1 divided by C2 can vary between 1/3 and 2/1, which are the coefficients x1 and x2, x1 and x2 for each one of the constraints. Which yield the following optimality range. So in this case, is 1/3 has to be less than or equal to this ratio, C1, C2, and this has to be less than or equal to 2/1, which is the same as saying 0.333 has to be less than or equal to this ratio, less than or equal to 2. So let's look at these questions. Suppose that the unit revenues for product 1 and 2 are changed to $35 and $25 respectively. Will the current optimal remain the same? The solution at C will remain optimal because C1 by C2 equals 1.4, which remains within the optimality range. The optimal value changes to 35 times 3.2 plus 25 times 1.6, which is equal to $152. Question 2. Suppose that the unit revenue of product 2 is fixed and its current value is C2 equals 20. What is the associated optimality range for the unit revenue for product 1, C1, that will keep the optimal unchanged? So if we substitute C2 equals $20 into the condition, then we can solve for C1. And we get the following. 1/3 times 20 has to be less than or equal to C1, and 2 times 20. So C1 has to be less than or equal to 40 and greater or equal to 6.67. Okay, so far we have started the discussion on sensitivity analysis for linear programs. In this first part of the discussion, we will focus on the graphical sensitivity analysis for linear programs. And obviously, when we use linear, the graphical method, we are keeping our models small, so they only have 2 decision variables. So we can illustrate graphically what's going on using sensitivity analysis. So we talk about the dual price, we talk about the shadow price, which is the same thing. And we also learn how to use those concepts to answer questions related from a managerial perspective. So in the next lecture video, we're going to focus on sensitivity analysis using the algebraic method, which will help us perform the same type of analysis and answer the same type of questions for problems that are bigger in size. So that's what's going to happen in the next lecture. So at this point, we're going to stop here and we'll continue in the next video.